Welcome back to another LeetCode with me session, where I again solve 2 random LeetCode questions, totally on the fly, including all my mistakes and kind of just showing you my process. And yes, I did get a haircut. Hopefully this proves to you that I'm not AI, despite commenters insisting otherwise. My hair does grow. For the very least, if I am AI, I have a lot of attention to detail to be growing my avatar's hair. That would be interesting. Anyways, no. I'm not AI. Crazy that I have to say that. Okay, anyways, let's get into it. A couple of videos ago, someone asked for a graph question. So we are going to start with a random graph question. Find the town judge. In a town, there are n people labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody, and everybody except for the town judge trusts the town judge. And there's exactly one person that satisfies properties 1 and 2. So there's exactly one town judge. Is that what it's saying? You are given an array trust where trust I equals AI BI, representing the person labeled AI, trust the person labeled BI. If a trust relationship does not exist in trust array, then such a trust relationship does not exist. Okay, so it's an adjacency list for a graph. Because this is a graph question, this is a wonderful opportunity to draw things out before we get started. So let me pull out my iPad. Hopefully my iPad recording doesn't lag like it did last time. So, for example number 1, we have n2. So we have 2 people, so 1 to n. So we have person 1, person 2. There's trust from person 1 to 2, so therefore 2 is the town judge. For n3, we have 3 people. There's trust from 1 to 3 and from 2 to 3. So therefore 3 is the town judge. And then for this one, there's trust from 1 to 3, 2 to 3, and 3 to 1. So therefore there is no town judge because the town judge trusts nobody. And everybody except the town judge trusts the town judge. I think they're also allowed to trust each other. So the idea is, first off, there needs to be at least one person who doesn't trust anybody. Okay, the person who trusts is the first person in the it's not a tuple, but so 1 trusts, and 2 trusts, but 3 doesn't. 1 trusts, 2 trusts, and 3 trusts. Therefore, there's nothing. My first thought is we can check against the first property where is there somebody who trusts nobody? And if there isn't, then automatically return -1. And if there is only 1 or more, actually, then we have to go on to check property 2, where we then go through and check that everyone other than that number has a trust relationship. And if there is more than 1 that we found for property 1, we have to check every single one of them, and if every single one of them also has property 2, then it's also -1 because there can only be 1, according to property 3. Okay, so our first step would be check who trusts nobody. Then, if no one, return -1. Otherwise, we will go on to number 2, where check if everyone trusts the person that we found in step 1, and we will have an array of that. It might only have 1 person, or it might have more, but check if everyone trusts each person in that array, and then if they don't, remove them from the array. And then by this point, there should be exactly 1 item in the array. So if the length of array is 1, return that item, else return -1. Okay, that's pretty straightforward. So let's think about, before we start, what's the time complexity of this? So we'll have to go through the adjacency list once to find who trusts nobody. And then we'll have to go through again for each person who doesn't trust any. Wait a minute. I just realized, if there's more than 1 person who trusts nobody, the answer is -1, because there can only be 1 town judge, and everyone else has to trust them. Else, if 1, continue. Else, if more than 1, return -1. So check if everyone trusts that person, otherwise return -1. Okay, check who trusts nobody. So what's the way we can do this? Well, the first thing that comes to mind is making a set of all the numbers to n, and then removing numbers from that set every time we find someone who trusts someone. However, that will give a space complexity of O of n. And then, oh yeah, we were talking about time complexity. What's our time complexity? So we have to go through once to find who trusts nobody, and then we have to go through again to check if everyone trusts number 1, or trusts the one we found previous. So O of 2n, so O of n. And then, worst case, O of n. And then space complexity depends on how we're going to store this. So the first thing comes to mind is, again, the set. We have no more than 1,000, so that shouldn't be too bad. Yeah, and you can't trust yourself. So I'm going to go with the set. Who trusts nobody? It's that. Okay. And then for relationship or for trust in trust, we're going to say nobody, remove the first element of that, right? Okay. And then after that, if length of nobody is not equal to 1, then we return -1. Otherwise, we go on and see, we're going to be bad and just reassign a set variable to an integer variable. I think we can index sets. This is such bad practice, but we'll see. And then we're going to say, no, actually, we're not going to reassign that. What am I saying? That's the judge. Does everyone trust the judge? We don't have trust here. So we go on and remove everyone who trusts. So for T in trust, if the person who's being trusted is the judge, no trust, remove T0. Yep. If no trust is empty, is that a thing? Set is empty. Oh, yes, implicit Boolean. If no trust, return -1, else return judge. See how many mistakes I made. What on earth am I doing here? Length of what, Anna? Okay, clearly I'm very used to ranging over lists, not straight integers. What? Wait, no. I know. Shut up. I'm not subscribing to premium. Right. Let's just say, how do we get first element set? Okay, there's no way. Arbitrary element from the set. Wonderful. That's fine. We can just pop because we only have 1 at this point if it didn't go to here, right? Yes. So we did well. We are outputting -1 every single time. So what went wrong? So we have n for n in range 1 and 1. So when n equals 2, we have 1, 2. N plus 1 is going to be 3. So we have 1 to 2, but range is exclusive. No? Still not? I really wish LeetCode had a way to see print out things. I think it's like a premium feature. Oh well, I guess we pull up VS Code. No Copilot, as always. For 2 there. And then what we want to do, first off, I want to print who's in nobody when we do that. 1, 2, and 3. That's not right. So I misspoke there. So it's 1 and 2, right? For that, we want 1 and 2. And then after that, we want to see what happens where we have 2. Are we returning here? No. Oh, we want the judge to have no trust. So if we want to remove the judge, then we want to do this. Does that give us the correct answer? Yes, it does. Yeah, so our problem was that we were saying nobody can have no trust, but the judge has no trust, so we have to remove the judge from that. Okay, what else did we... Oh, yes. We also undid that. There we go. Let's see. No. Oh, yeah, so... I have to check this. Okay, there we go. So we used 15 seconds of runtime and 7 milliseconds is the better one. Okay, pretty much around the average for memory. We could do, I wonder if this will make a difference. I really don't think it will. If we do that instead. Okay, it made a very small difference, but that could be totally incidental too. Okay, not bad, not bad. I'm curious what happened here. In, out. Oh, so we're counting in and out relationships. So it needs to be that for everyone, if the in is everyone except them and the out is nobody, return that person. Otherwise, return -1. Okay, so that's a little bit more of a very graph-oriented approach of just thinking about what's the term for it? Whatever the term is of counting the number of paths out and paths in to a certain node in a graph. Yeah, in degree, that's what the term is. Okay, so now we're going through the list twice. We could go through the list once instead. And I think that would especially help on memory. Okay, makes sense. That's cool. Okay, quick pause before we go on to the next problem. This video is again sponsored by FlexiSpot, and we have got to talk about this chair. So, before this, I was coding / doing things at my desk on a Walmart dining chair. And I was starting to get back pain so bad that sometimes I couldn't even bend or sit down properly. And I'm way too young for that. I'm 20. But the shrimp posture, it's what gets you, especially us coders. So I knew I needed to upgrade at some point, and so huge thanks to FlexiSpot for sending me this Ergo X Pro office chair. Timing could not have been better. The lumbar support actually hits where your lower back needs it, and it's adjustable. The headrest is totally adjustable, so you're not craning your neck forward, and you can even remove it completely if you don't want it. The armrests are very adjustable too, so height, forward and back, swivel this way, swivel that way. The seat height is obviously adjustable, as well as recline angle, but honestly, just sitting in a chair that's designed for long sessions makes it way easier to stay focused instead of constantly shifting around trying to get comfortable. And I say this honestly, like off script, I am legit excited to sit down and do my work just because of how comfortable this is. So if you're also out here coding on a dining chair or something equally cursed, the link is in the description. I have an affiliate code, so check it out. Okay, let's go on to the next problem. Random. Count ways to build good strings. Given the integers 0, 1, low, and high, we can construct a string by starting with an empty string. Then, at each step, perform either of the following. Append the character 0 times, or append the character 1 time. What? Okay, so 0 is an integer, and then we can append it that amount of times. Oh my gosh. The naming of these is already throwing me off. Append the character 1 times. Okay, let's think. So 0 is just, it's called 0 because that's the number of times we're appending 0. Not literally, it's the number 0. Okay, we can construct a string by starting with an empty string, and then at each step, append the character 0 times, append the character 1 times. A good string is a string constructed by the above process having a length between low and high. Return the number of different good strings that can be constructed satisfying these properties. Since the answer can be large, return it mod 10 to the 9 plus 7. Okay. Input low, 3, high is 3, so we want it to be exactly length of 3. 0 is 1, and 1 is 1. But there are 8 different ways to do that. One possible 0, 1, 1, 0, 0, 1, 0, 1, 1. All binary strings from 0, 0, 0 to 1, 1, 1 are good strings. Okay. Is that a clue? We'll always be having binary strings. Low is 2, high is 3, so we can have any length between 2 and 3. So we can have 0s 1 at a time, and we have 1s 2 at a time. So we have 5 different ones we can do. Okay, I'm just curious what topics this falls into. Is this a DP sort of thing? Yes, it is a DP. Okay, no, it's okay. I literally took design and analysis of algorithms already last quarter. So let's see if I learned anything in that class. Not like it was my lowest grade in my entire transcript. Okay, so, oh gosh, low-key, this is a lot of pressure. I'm gonna cry. No, I'm not, it's fine. So, since this is a DP, does that mean we're gonna do a DP table? Honestly, I'm figuring this out as we go along. Because, okay, this is kind of embarrassing, but I don't think I've actually ever solved a DP question on LeetCode. I might have. We'll see. We'll see how this goes. Well, actually, do we need a DP table? So my first thought when reading this is we have a choice at every step. We can either do 0 or 1 of however many we're allowed to do. Either 0, 1, or we stop. So for this first one, we start with an empty string. Then we can have a 0 or a 1. We can't stop at that point. And then at that point, we can have another 0 or 1. So 0 or 0, 1. And we can have that 0 or 1, 1. And then the length is 3, so we keep going. We can either have 0, 0, 0 or 0, 0, 1. I mean, this is a pretty this first one is pretty straightforward. It's like, as it said, every binary string of length 3. Okay, so that's our 1, 2, 3, 4, 5, 6, 7, 8 outputs, right? So at that point, we stop. For a second example, we can stop when a string is 2 or when a string is 3. Again, first we either pick between 0 or 1. 0 will have 0, 1 will have 1, 1. Then again, we pick between 0 or 1, so 0 or 0, 1, 1. At that point, we can stop because we are at length of 2. And here we have to stop because we're at length 3. Here we can add another 0. We cannot add another 1 because that will put us at 4. And then here, so 1, 1, we can then go 0 or 1. So that'll be 0, and then we can't go that. We have to stop here, or we can stop here. So at that point we have 1, 2, 3, 4, 5 different ways. Yes. So I think we have the sort of procedure down. How do we make that into code? So let's think about the patterns here. We only want to know the number of different good strings. So maybe what's the minimum tree depth at which we start having things, and what's the maximum tree depth? So the minimum tree depth is whichever 0 or 1, whichever one is the highest. So here, for example, it's 1, or the low divided by, how can I make this more clear? So the low divided by the maximum of 0 or 1. So at this point, its low is 2, so the minimum depth is 1, because here we see that at depth 1, we actually have already one of our first n solutions. If the low was 3, 3 divided by 2 min depth is 2. Yeah, that makes sense. And then our max depth is going to be our smallest between 0 or 1, and how many times it takes to get to the high for that. So high divided by min 0, 1. So that's the difference. I mean, I guess we could do this recursively, in which we find every single good string that we can, and then, so what I'm thinking is recursively we can build out this tree, or send recursive calls down this tree and stop them when they are no longer allowed. We're like, adding more things won't help you. Okay, I'm definitely pulling out VS Code for this one because I want to see what I'm doing as I go along. Obviously, in interviews, this isn't a guarantee, and a lot of times they do want you to just like code it and dry run it, and you get no IDE and you don't get to run it for reals. But as I said, embarrassingly to admit, I have not done a DP problem for a while, so we are going to take it a step at a time. We're going to make a recursive function that just finds every single good string. It's probably not the most optimal solution, but it's the one I want to try. So what exactly are we doing? Let's just do this all in comments. So we can either add 0, add 1 recurse. So our base case is if we've reached our high. Or actually, what do we even want to return? If we are above our low, we want to add that to whatever we're doing, above or at low. If at high, we don't recurse actually. So let's say our string is empty. We would do find good strings for our string plus 0 times 0. And then we want to do that 1 times 1. Okay, if we're above the high, we're done. Otherwise, we recurse. We will have to add low, high, 0, 1. Okay, let's just put this into VS Code real quick. Let's just say print string. And then I want to see what happens so far where we have nothing. Our low, let's say, let's use this one. Low is 2, high is 3, 0 is 2. So let's see what happens. So we have 0, 0, 0. We have 0, 0, 1, 1. Right, so if the length of the string is at or above low, then we want to be added, right? Okay, so that's our 1, 2, 3, 4, 5. All right, so we're finding our good strings already. So now we're printing them out. So all we need to do is count them, right? I think we just added total. Then we just added self to there. No. There we go. Find good strings of empty string, low, high, 0, 1. Then we want to print the solution of that. Actually, no, we want to print solution of count good strings of that. And then we're just going to say solution is 5. Perfect. Okay, so that is doing what we want it to do already. I feel like this is deceptively simple now that I've done it. So let's see if it actually works in the broader context. Output limit exceeded. Indeed. Oh my goodness. Okay. So what did we say our length answer can be large? So mod of that. What would that help? That is a very random, I feel like anyways, that's a very random thing to do. Oh, and also we don't need to be printing because output limit exceeded. Yeah, we don't even need to have an output. Time limit exceeded. Yeah, that makes sense. No, we're gonna have 200 ones. We can have 20 zeros, 20 times 10 zeros, or anything in between. I just want my first solution to work. Why won't my first solution work? Okay, what can we do to make this better? Why is it taking too long? Well, I think the most obvious answer to that is the fact that we did not use DP. We do not have any sort of memoization or caching. How could we do that? Okay, fine, we'll make a DP table. If I can remember how to make DP tables. So what is our difference? So if I can remember this correctly, if we have a length of 0, 1, 2, I'm just gonna make one for this one because I think that's the easiest one. For example, number 1, 0, 1, 2, 3, that's our length. Let's think about this. How many strings can we get of length 0? 1, the empty string. How many can we get of length 1? We can get 2, either 0 or 1. How many of length 2? We can get 0, 0, 0, 1, 1, 0, 1, 1. How many can we get of length 3? 0, 0, 0, 0, 1. Then obviously the entire thing. Okay. I think I have an idea of how to do this. So first off, basically we build up our dynamic programming table. Basically this, just 0 is 1, 1 is 1, 2 is 2, and 3 is 3. And then we start from the end. And our maximum length, let's say, is 3. So we start from the end and we have something something ending with 0 or something something ending with 1. We're ending with 0. Our length is 3. And then we just take the 0 off. We now have a length of 2. And we go back 1. If we have something something 1, then we know that there has to be 2 1s there. So we take them off and then we now have a length of 1 and we go back to there in the DP table. Our first step then is to build the DP table. And then our second step is to use it to go back. So how will we build our DP table first off? Well, obviously when we're building our DP table, do we want to be using our previous stuff? Yeah. At DP 0, it's 0. No, DP0 is 1. We have one way to do a length of string length of 1, and then DP1, we have one way to do it. It's the 0. 2 is going to be 2 ways. So then here, DP2 is going to be something something. If it ends with 1, because there's this, we have to go back and do that. And if it ends with 0, then we go back to here. So it's 1 plus 2. So it's either that or it's that. If it's this, it has to be this. And if it's this, we go back to here because it can be anything. And there's one way. So it's 1. So 1 plus 1 is 2. Then after that, we've passed our maximum between 0 and 1. So for DP3, it'll be something something 1 or something something 0. Well, let's just be in order. Something something 0 or something something 1. Let's just say it can either end in 0 or it can end in 1, 1. So for this one, we go back. We have 2 question marks, so DP2 is 2. And then we have 1 question mark, DP1 is 1. So 2 plus 1. And then, of course, that's as far as we would go, but just for practice, let's do one more. So we can either end with 0 or we can end with 1, 1. Then we would have 1, 2, 3 before that and 1, 2 before that. So we have 3 unknowns here, so that's DP3, which is 3. And then we have 2 unknowns here, which is DP2, which is 5. Okay, I think we're starting to get it. So first we have an array that is of length high, in range of high. So, no, our high is 3, so it's 1, 2, 3, 4. So it's actually high plus 1. Then, of course, our DP at 0 is going to be 1 always. Okay, so in both examples, we have at least 0 or 1 being of minimum length 1. However, what would happen if we had it, let's say, what if 0 was 2 and 1 was 3? This is such confusing terminology, but so if 0 was 2 and 1 was 3, and let's say our low was 5 and high was, I don't know, 6. In that case, our 0 would be, again, we would have one way to do that. For 1, we check, do we have 0 or 1 equaling 1? No. Do we have 0 or 1 equaling 2? Yes. So I believe for I in range, until we get to the minimum of between 0 or 1. So in this case, in range 2, there's no way to do that. To have a length of 2, we have to have 2 zeros, which is one way. For a length of 3, we can either end with 0, 0 or 1, 1, 1. Yeah, I feel like the starting point, getting past this hurdle of either 0 or 1 is too big to even have enough. Actually, for I in range, let's say we're going through a DP list. The I is greater than 0, then we can add. Then if I is greater than 1, greater than or equal to actually, then we can do stuff. So what is the stuff that we can do? I is greater than 0. 2 right here is greater than or equal to 0, which is 2. We can then go I minus 0 plus 1, and that's the amount we can add to there. And then also, that's the amount we can add to here for 1. So for example, here we have 0 is 1, that's here. Then for starting from 1, if I is greater than 0, it's not. If I is greater than 1, it's not. For number 2, if I is greater than or equal to 0, it is. dp2 is going to be equal to 2 minus 2 plus 1. So plus equal 1. dp is greater than or equal to 1, it's not. So for 3, if 3 is greater than or equal to 0, it is. We go dp3, we add 3 minus 2 plus 1. Not plus 1. This time it's not plus 1 because this time we only want to, for 0, add that there's one way to do that. No, there's no way to do that actually. There's no way to do 3. Oh, at this point is where we actually want to go, it's a dp I minus 0, not plus 1. So 2 minus 2 gets us to 0, which is 1. Right? Okay, then 3. 3 minus 2 gets us to dp1, which is 0 right here, because this is not possible. And then if I is greater than or equal to 1, we have 3. 1 equals 3, so that passes. So 3 minus 3, yeah, so there's one way to do that. Okay, so then that ends up being 1. And then for number 4, then we have both of those going for us. So again, 0 is 2, so 4 minus 2, dp2, it's going to be 1. And then in 1 is equal to 3, so 4 minus 3 is 1, 1 plus 0. So there's only one way to do that, which is 0, 0, 0, 0. Okay, yeah. I think this is making sense. For I in range, starting from low, ending with high. So we want to end with high inclusively. We want to add to the result. dp I. And then we return. Is that going to work? Okay, it's going to work. Oh my goodness, is this the answer? Only thing we forgot is to do the mod. What's the mod again? 10 to the 9 plus 7. Well, we solved it. Terribly, but we solved it. Okay, what did we do here that made it so bad? Resubmit? Yeah, no such luck. I'd like to know why I make M ways. So what is this M thing that they're doing? Oh yeah, so I think the answer to that question lies at least partially in the fact that we're modding things at the very end, and that's not actually helping us with our calculation. So where are they actually modding this? So is it our list comprehension that's doing badly? Because there's probably a better way to do this than this, right? So let's just experiment. High plus 1. What happens when we do something like this? Okay, so that's exactly what we want to do, actually. It is still plus 1. I'm just curious how much this will make a difference. Not significantly. So what's actually making the difference for something like this? For memory. So ways is their DP, right? And then I think it's the mod. Yes, back to that. Why is it that we're only modding on that? And also, what is this? We don't have, so we have 0 that, 1 that. Yes, but we don't have if I is greater than or equal to low. Oh, I think they just condensed this into here. But what's this? Why are we modding it here and not here? That's what I want to know. Will this still do the correct math? Because that makes sense. And then if we do this, that's the only thing, that's the only other mod place that they had. What? You're telling me that was it? Okay. I guess that makes sense. No, that makes sense because we end up having numbers that were way too big. My only concern with not implementing that in the first place was if the math would still work out with this kind of thing. But no, it does work out because you would only be adding things and it's on a loop. I don't know if that makes sense, but it's making sense in my head. Let's go. Okay, we did it. I'm gonna high five someone right now, but I have no one, so yay. All right. That is a wrap on today's LeetCode session. As always, let me know how you'd have done these down in the comments. And also, I normally pick random questions to do, but let me know if there are any particular kinds of problems that you'd like to see more of. If this is your first time, I do LeetCode with me every other week, and otherwise, I'm just sharing my journey as a computer science student here on this channel. See you next time.